Welcome to Reliability Matters, a podcast for the electronic assembly industry. Each episode covers topics related to reliability, best practices, and environmentally responsible assembly techniques, with insights from experts across the electronic assembly industry. Now, here's your host, Mike Conrad.
Well, welcome back to another episode of the Reliability Matters podcast. And once again, Happy New Year. My guest today is someone who's been on the show before, Tony Lentz. Tony's worked in the electronics industry since 1994. He entered the industry as a process engineer at a circuit board manufacturer, worked on the dark side of the business, as we would say on this side, and worked there for about 5 years. Since 1999, Tony has worked for FCT Companies as a chemical laboratory manager, a production facility manager, and most recently a field application engineer. Since 2013, Tony is focused on solder and stencil products, which is something we're going to be talking about today. Tony has extensive experience in research and development, quality control, and technical service with materials used to manufacture and assemble printed circuit boards. Tony has published and presented many papers. He and I have teamed up and produced some workshops around the country. I love working with Tony. He's a wealth of information and a great presenter, as you'll see. Tony is a speaker of distinction with SMTA and participates in IPC J-STD-004 and J-STD-005 standards task groups. Tony holds a Bachelor's of Science and an MBS degree in chemistry. Tony was my guest way back in episode 32. That was 56 episodes ago, where he talked about stencil design and void reduction. Today we're going to stay on a similar theme for reliability, but we're going to switch the theme to something a little bit to the left or a little bit to the right. And without any further ado, hi, Tony. How are you?
Doing well. Thank you, Mike. Thanks for having me on the show.
Well, thanks for agreeing to be voluntold again. So I appreciate you being here. So today we're going to talk about another printing defect. I don't know if it's really a printing defect, but certainly the printing process can contribute to it, and the printing process can solve this problem. So without, I should probably describe what the problem is rather than talking around it, and that's tombstoning. And Tony wrote a great article, which I love the title, Tony. What do you want on your tombstone? I want a date a long time from now on my tombstone. But tombstoning, of course, is an issue that we see in the surface mount business. Tony, let's start with the very basics of what is a tombstone.
Well, a tombstone is where a component shifts out of its intended position. As you'll see in this video here, these components are, during reflow, the wetting force on one end is different than the other end, and it tends to pull the component out of position. So tombstoning is what you just saw there, where a component stands completely vertically on its end. There are related defects. One is called drawbridging, where the component only lifts partially vertically, so it's only at an angle with respect to the circuit board. And then there's just shifting or skewing, which are also positional defects, where the component ends up out of its intended place.
Yeah, that's a fascinating video. Watching that come up like that. Now I know that there's other types of phenomenon, all related to a component standing up or otherwise. Tell me what the other phrases are. One of them was a billboarding. So we have tombstoning, then we have billboarding, and
billboarding, yes, that's where the component flips up on its side, but it's still making contact on both ends in terms of like passive components.
So it could pass a functional test because it's making contact, but it certainly doesn't have a lot of intermetallic bond because it's on the narrow end of the component, right?
That's correct. Yeah, and in that case, the solder joint mechanical strength might be compromised.
Right. And then there's a drawbridge. Was that one of them? Is that where it just kind of comes up at maybe a 45-degree angle, but not quite 90?
Yes, drawbridging. Yeah, we have all these creative terms for this defect.
I love it.
Drawbridging, yes, it lifts part of the way up, but not completely vertically.
Yeah. And I guess the worst, well, maybe not the worst, but maybe the most insidious defect is one where you still have contact, an intermetallic contact. So the part might function, but it might barely function. I saw earlier an example of an LED that was so skewed, still making contact, but so skewed that it didn't light properly. That's another one too. All right, so let's talk about the causes of tombstoning, billboarding, drawbridging, skewing, all the things that happen. What are some of the causes for this? And then kind of we'll get into what some of the proposed remedies are.
Well, like you mentioned, most of the causes for these types of defects might start at the print stage. So when you're designing the stencil initially and designing the pad set, that affects where the solder paste is printed, obviously. And quite often, these designs for components include a pretty large area of solder paste coverage relative to the size of the component pad that it's making contact with. And so there can be a relatively large wetting force of the paste as it wets up the end of the component. And that is the main driver that's going to draw those components out of position. And so I think it has to do partially with the relative mass of solder paste relative to the component mass, and then also the amount of solder paste that is wetting that surface.
So we're going to get into a DOE that you put together relative to tombstoning. But before we go down that road, I want to learn a little bit more about tombstoning. You talked about some of the causes of tombstoning and other similar defects. Does solder paste selection influence tombstoning? Can someone choose, quote unquote, the wrong solder paste, which exacerbates the propensity of this particular defect?
Yes, actually, solder paste has a big part of it, as does pad design, which I'll go into in a little bit. But the solder paste selection itself definitely influences tombstoning in two ways. So solder paste fluxes that are less able to wet the surface that you're soldering to, like for example, if you have an OSP coated circuit board, certain solder paste wet that a little better and faster than others. And if you have a slow wetting speed and the solder paste doesn't spread very quickly, that tends to reduce the potential for tombstoning. If the wetting speed is fast, like with higher activity solder pastes, then that can exaggerate the problem by wetting one end of the component much quicker than the other and shifting it out of position. Or one set of pads on the bottom surface of a bottom terminated component might shift it out of position that way. And then the alloy itself plays a role where eutectic alloys, which melt and freeze at one temperature, tend to lend themselves more to tombstoning related defects than other alloys. So eutectic alloys, because they melt all at one temperature, for example, like classic 6337 tin lead, 37 tin lead, the entire mass of paste will go liquidous at one time. And then the wetting all happens at one time, which tends to, again,
you don't have that plastic, that sludge state, plastic state, right?
Right.
And during that plastic state, I would imagine everything, surface tension's different, all this stuff is different, and it may cause the part to maybe even float a little bit more in this sludgy kind of state. Is that phenomenon real?
Yes. Yeah, certainly. Mm-hmm. Having a sludgy state in the solder paste definitely helps to reduce the potential for the problem. So one solution to the problem, which we'll get into later, would be to switch the alloy that you're using in the solder paste.
Yeah, we'll go down that road because I do have some questions about switching alloys. But let's go down the question list first so we don't put things out of order. Are there specific types of components that are more susceptible to tombstoning and other skewing kind of issues?
Yes, certainly. I think in the world of print related problems, usually it's larger passives that we see the issue with. So 0805 sizes and larger tend to be more susceptible. And also capacitors rather than resistors are more susceptible because capacitors tend to be built with a taller profile. And so the component height is a little larger and there's a higher center of gravity on those type of components. And there's also an issue with just generally speaking, like large power supplies, large bottom terminated components that maybe have a real high profile. And those tend to want to shift or move during reflow. And then, of course, other bottom terminated components like LEDs, QFNs, all of those types of components can tend to skew or shift during reflow.
Right. I would imagine this. I don't think this was a subject of your DOE or the presentation, but if a LED in particular skews and still maintains contact on both sides, I think thermal dissipation is an important element, maybe even more so on LEDs than other components. And am I right in assuming that one can lose the balance of thermal dissipation if you're just soldered to one tiny edge of one side of the LED and not the other?
Yes, certainly. Yeah, certainly. The less contact area you have with the soldered joint obviously is going to not be able to transmit heat as effectively out of that component. And so
Right.
thermal
An LED
failures
more
are
than
a
any
real
other
problem.
Right, and LED more than capacitors or resistors are really sensitive to for heat dissipation. They require heat dissipation more than other types of components. I believe. Is that correct?
That's correct.
Yeah.
Yeah. The main transmission of heat away from LEDs is through usually one of the solder joints.
Right. Okay, let's talk about the DOE. First of all, what was the driver to pick this subject? You're in this business, so I don't know. Are you just getting calls all the time? You know, did you get one too many calls and you said, okay, we got to solve this, or what was the motivation for this?
That's a great question. Actually, we do get a lot of calls about this. Yeah, both FCT and blue ring stencils. So we deal with this problem from different approaches, obviously. My counterpart, Greg Smith, who helped work on this paper, deals with it from a stencil design point of view quite often. And then I get calls from the solder paste point of view or reflow profiling point of view. And we often team up and work on these issues together to help solve this problem for customers. Usually you can deal with this through some combination of stencil design, solder paste, and reflow profile change. But like you said, we'll get to that later.
Yeah. Okay, so tell me about the DOE. What was the basic layout of the DOE?
So the idea here was to try to create pad sets that were representative of typical layout. So first of all, we have standard pad sets for 0805 and 1206 components. And then we threw an LED on there, which happened to be a 3-terminal LED. And so we made a standard pad design based on the component data sheet. And then the other pad designs were shifted out away from each other. So we actually took the pads on the board and moved them apart from each other in order to simulate what happens if the pad layout doesn't exactly match the component type. Because we see that quite often where, especially with supply chain issues today, where someone might substitute, say, a smaller component for a pad set that might call for a larger component. Maybe somebody's put in an 0603 and an 0805 pad set. And so the component pads barely make contact with the actual board pads. And therefore, there's a lot of solder paste mass outside of the body of the component, which will exert a greater wetting force and cause the potential for shifting or tombstoning. And so that was part of the board design. The other part of the board design is we wanted to make it with relatively heavy copper weight. So we had 2-ounce copper plane on the top surface and then a 2-ounce copper ground plane on the bottom surface. And we connected the top surface to the bottom surface with via holes, plated through vias. Sorry, my earbud's falling out.
They always do. Mine loop around my ear, so they attach in. But I can't tell you how many times I've had a guest with it just falls on the table.
I had this one in the wrong ear. That was the problem.
Oh yeah, left and right for a reason, right?
Yes. Yeah. So the other part of the board design that we worked on was to create like a thermal mismatch. And so we wanted to have one end of each component on a ground plane that was connected to the bottom surface of the board through plated through vias. And so there's a lot of copper there wicking heat away during reflow on one end of each component. And the other end was on an isolated etched pad. So that's the other commonality we really see with tombstoning. When boards are designed that way, which is pretty typical, where one end of a passive is on a ground plane and it's a solder mask defined pad, and the other end is on an isolated etch pad, those heat up at different rates during reflow. The isolated etch pad tends to heat up quicker, and then the solder paste reflows first, and sometimes that'll skew the component. Or sometimes the solder paste on the other end, which will reflow second, will then exert a bigger wetting force and skew the component. It just depends on how much paste is going down on each end.
Mm-hmm. If a component is not centered properly over the two pads, if it's skewed a little to the left, a little to the right, there seems to be some kind of little tug of war going on with not gravitational forces, but intermetallic forces. They're pulling one side to the other. Is how important is component placement and symmetry with avoiding skewing issues? Do things have to be perfectly centered so that there's an equal amount of contact? And if so, not all components have equal amount of landings on each end. Some require larger pads on one side than the other. So how does all that kind of play into it?
Well, components don't have to be perfectly centered. There is a self-correction effect that'll happen pretty naturally, where the solder paste wants to flow to the solderable surfaces. So it wants to flow back to the pad, and it wants to wet the component and pull it back into position. But in some cases, if the components are, if the pad layout is too far apart and the components aren't making contact with one pad during placement, or if there's placement errors and the components are being placed off target just due to equipment capabilities, like for example, if someone's using old pick and place equipment that was designed for 0402 size components and they're starting to place 0201s or smaller components, that may not be repeatable and it may not be precise in where it's placing those. And so those just being off target just enough, they may not self-correct during reflow and they may go the other direction and lift or skew.
I think that was one of the examples that you had in your DOE. You had the pick and place machine wasn't able to place a certain size component, so you substituted it for a different component. This was intentional, I believe. Tell me about that, if I got that right.
We have a basic pick and place, let's to put it nicely. It's a tabletop lab scale pick and place system, and it really isn't capable to place 0402s or smaller. And so initially we designed this test board with 0402s and 0201s, and we had good intentions of using smaller components, which seemed to be more susceptible to this defect because of placement error potential. But our pick and place just wouldn't even place them near where we needed them. It was off target. It was actually the blow off in our pick and place tends to shift components around. And so we found that the 0402s and 0201s were getting blown around and way off target. So we couldn't even get reliable data off those circuit boards. So we redesigned the board and used larger components for that reason.
Okay. So that wasn't really, there was no aha moment by changing a component size and keeping the pad the same. You redid the whole, kind of redesigned the assembly for that purpose. Okay. I was thinking that you'd stumbled across a aha moment where if you take one size pad and put another size component on it, everything disappears, right? All the problems go away.
We did try that as well, but we tried that with the intention of going in the direction to cause the problem. So we were trying to cause tombstoning. And honestly, the first board design, we completely failed at causing tombstoning because we couldn't place the components repeatably. But during the second board design, what we saw was not really a lot of tombstoning, but we saw a lot of shifting and skewing, which is also more prevalent than tombstoning, honestly. Tombstoning of a strictly vertical nature isn't that common. It's more shift, skew, maybe a little lift that occurs.
Yeah, it's always frustrating when there's a constant problem you're trying to solve. So you do a DOE or some kind of paper on it. Now you can't make the problem happen. The secret is if you never want tombstoning, just make every project a DOE and it'll just never happen, right?
Exactly.
So tell me how stencil designs can influence negatively or positively. Positively is where we're going for the reduction of tombstoning and other related reliability issues.
Stencil design can have a great impact on that. We normally will start there by looking at the stencil design if the customer is willing to change stencil designs, and in some cases they can't or they aren't able to. So what we try to do is for like passive components like 0603s, we'll move the solder paste print so that it's a little more under the body of the component, or we will remove solder paste from the outer edges of the print. So we'll actually create what we call a U-shape or a reverse U-shape. So we're actually removing solder paste from those outer edges of the pads, so there's less mass and less wetting force on the ends of the components. Or it also delays the spread of the paste. So the paste has to first spread to the end of the pad, and then it can wet up the end of the component. So it slows down that whole wetting process.
And I think what we're seeing on the screen here is an example of your reverse U.
Yes, for this test board, that was the example of our reverse U.
For those in our audience who are listening to this episode in the car or on the treadmill or wherever you listen to your podcast, and wondering what the heck are they talking about, I'll encourage you, in this particular episode more than others, we have a lot of visual assets in this episode. We have some screen grabs from Tony's presentation, and right now we're looking at what a reverse U stencil design looks like, and there's a few other examples. You heard Tony reference a video earlier as well. So I'd encourage you, if you want to get a little bit more out of this particular presentation or this particular conversation, go to our YouTube channel if you're not already there, and it's the Reliability Matters YouTube channel. You can just search it in YouTube, and you'll be able to see this particular episode and in all of its glory, in all of its video asset and photographic asset glory. So by having this reverse U, that causes the solder paste to cause a more directional pull or less pull. What's the kind of the physics behind that?
So the physics are the solder paste is, like I said, been removed from the outside edges of the component. And so there's exposed pad base metal there. And so the solder paste has to first wet out to the end of the pad before it can really make contact with the end of the component and then flow up the component end. So it slows down the whole wetting process, and then therefore also exerts, you're actually removing area of coverage of solder paste in this case. So there's less mass of solder paste. So there's less wetting force on the component itself.
Mm-hmm. Interesting. Now there are other little tricks you have up your stencil sleeve. What are some of the other tricks one can do with stencil design, if that is an option open to someone looking to solve this problem?
Well, if you're talking about something like a bottom terminated component, quite often what we found is the pads designs, especially on like LEDs, are not equivalent. So they're not well balanced. The pads can be, usually there's one smaller pad and one really large pad, or two small pads and one large pad. And so just by the physics of how the solder paste has to wet those pads, there's unequal force on that component. And it really has a potential to skew. And so by breaking the solder paste print up with webs in between of unprinted area, or window painting, something like that, like what you're showing on the screen there. So if you can break the solder paste print up, then that will help minimize the amount of force the solder paste is exerting on the bottom of that component. It also slows it down. Again, the solder paste has to fill in all those gaps before it exerts its full force on the component body.
Okay, interesting. So there are some good stencil tricks one can do, but not everyone. We're going to come back to the DOE and how these changes affected the amount of tombstoning. But I have 100 stencils in my catalog, and I don't want to go back and redo 100 stencils because that's really pricey. What are some of my other options? I can't make stencil change designs, at least not right now. Too expensive. But there are, for example, different solder pastes that I can go to. You talk about kind of anti-tombstoning solder paste. This is kind of a Tony guess here, but from a percentage standpoint, by just changing solder paste, no other physical changes, no changes that cost money. If you're buying solder paste A, you can buy solder paste B for about the same price, roughly. Mm-hmm. So changing solder paste materials to a quote unquote better anti-tombstoning solder paste, from a percentage standpoint, how much do you think that could reduce the problem? Does it make 90% of it go away? Does it reduce it in half? Is it just too hard to tell? Is that a hard number to pin down?
What I've seen is that, like you said, when in the situation where folks have stencils that are in stock and they don't want to go through and redesign every component layout on all the stencils, which is very costly, then switching solder paste is an easy change, like you mentioned, because there's no cost difference typically between any tombstoning pastes and regular solder paste. And that, for a lot of our customers, has been a great solution. And I would say it solves more than 75 or 80% of the tombstoning defects. It gets it down to a workable level where they're not having to rework too many components.
Right. Okay. So you can get a good stab at the problem by simply changing materials. And then if you want to make it go down even further, perhaps even bring it down to zero defects, then some of the other tricks can be implemented, stencil design changes, things like that. Walk me through kind of the conclusions of your DOE, if you would, and maybe through some of the DOE steps. Tell me where you started, where you ended, and what the takeaway was from all this.
Okay, so the DOE, like I mentioned, we were talking about the board design earlier. So we designed a board intentionally to try to create tombstoning. and it was a typical 0.59-inch thick FR4 material, 2-ounce copper weights. So the whole intention there was to create thermal differences from end to end of the component, but also have different pad sets for these components. And so we ran 10 boards per run, placed all the components, and we were expecting to see tombstoning wherever, especially on the shifted out pads, like what this diagram is showing here. But we were expecting to see it just due to thermal differences alone. And so we started off with a linear ramp to peak profile that was pretty short and fast, so pretty high ramp rate, in order to generate thermal differences. So that one end of the component, the solder paste, would reflow first. That was the whole idea. And then when we started running the DOE, we found that, well, we weren't generating a lot of tombstoning. Let's just put it that way. We were getting a lot of shifting and skewing on certain component layouts, but it wasn't the kind of numbers that we were hoping to see. And so we did some things where we changed the stencil design and increased the stencil thickness in order to generate higher solder paste volumes, in order to exert more wetting force on those components. And then we also went and ran a different profile. We ran a soak profile as a quick test to see if we could eliminate the small tombstoning and skewing that we were seeing. And the soak profile actually had no effect on the defect in this case with these test boards, which is unusual because normally switching to a soak type profile will have some effect. It'll reduce the occurrence of the defect, but it may not eliminate it. And so we threw out the whole idea of running a soak profile or running different profiles as part of this DOE. And instead, we just ran different stencil volumes to simulate what would happen. And then in one particular isolated test, we took the 0805 components and we placed them on the 1206 pad sets to really make a worst case scenario. Will these things skew if they're placed on a larger pad set? And that's just simulating like if a customer substitutes components and they can use an 0805 in place of a 1206.
Which may be happening a lot these days. Mm-hmm. Which may be happening more today, substitution of components, than perhaps in the past with the chip shortages and supply chain stuff, right?
Yeah, certainly. And so that's what we were trying to simulate. And we saw some pretty dramatic effects of doing that.
Interesting. What, in your mind, would be the most effective of the changes? Were you able to, in this DOE, were you able to implement one change, see the results, and then another change, see the results, or was it all done kind of at this, did you incorporate the reverse U and window painting kind of, all in one? Sometimes you don't have the luxury to spread it out because it would be a year-long DOE, but was there a conclusion as to what move would be the most effective, or is it a combination of alloy and all the tricks in the book?
Well, that's a great question. Thank you for asking that. First of all, once we were able to create some shifting, then we could count the defect rate. And then we were able to make changes after that to try to reduce it. And so one of the things we did is run the reverse U stencil, which had a small impact. It didn't have a major impact. And we were able to run anti-tombstoning solder paste, which had a slightly larger impact. We're changing the alloy composition of the solder paste. So that's anti-tombstoning solder paste in this case was the same solder paste flux. So it had the same activity, same wetting potential, but we changed the alloy from SAC 305 to a mixture of SAC 305 and an SN100 CV alloy, which is a tin copper nickel bismuth alloy. But the point of doing that is to create a wider melting range where SAC 305 melts from 217 to 220 C. And by adding in a little SN100 CV solder powder to that mix, it then melts from 217 to 225 C. So we slowed down the melting behavior so that the solder paste maintained a pasty range or a tackiness to it during reflow.
And that helped in the reduction of defects?
It did.
Is an alloy like that available out of the box, or is this a little Frankenstein mix behind the curtain?
It is not normally stocked. Like we work with stocking distributors, and it's not something they would stock, but it's something that we make and sell regularly to customers who've had tombstoning problems, and they just buy it as a standard solder paste for all of their assemblies.
Interesting. Maybe that'll be the next big thing, right?
Well, some of our competitors do something similar. I think most of our competitors have an anti-tombstoning version of a solder paste, and usually it's an alloy change rather than a flux change.
So it sounds like the most effective the way these anti-tombstoning alloys work is just to stretch out the point to liquidus, right? To delay that as long as possible, to have more time in this sludge plastic state, and to slow it down so that it has time to settle and end up in the right place, for lack of a technical term.
Yeah, something that we didn't test was surface finish and nitrogen atmospheres in reflow. But in the literature search that I did, and you can read about this in the paper if you're interested, but there was a test done by other authors for different surface finishes. And OSP versus ENIG was tested in the potential for tombstoning, and they found that ENIG had a much higher incident rate of tombstoning than OSP, because OSP is much slower to wet. So most solder paste will spread more slowly over that surface. So that's what we're trying to do with anti-tombstoning alloys as well. The same thing is true with nitrogen in reflow. If you're using nitrogen, you're slowing down the whole rate of oxidation of the solder powder particles and the surfaces that you're soldering to. And if you can slow that down, then the flux doesn't have much work to do, and therefore everything wets and flows faster. Whereas if you're using an air atmosphere, which most of our customers do, you've got a lot of oxidation occurring during reflow, and then the flux has to deal with that oxidation, and it slows down the wetting rate. So nitrogen atmospheres tended to create more tombstoning because there's a higher rate of wetting or higher speed of wetting.
Does it make sense to purposely, when you're placing components, to purposely skew them, particularly for unequal pad sizes, so that knowing they're going to skew to the left or skew to the right, does it make any sense to not place them quite center? Anticipating a skew, is that a normal part of the process? Is that something that is documented somewhere, or is that just kind of a trick people know after years on the floor?
I think it's sort of a learned trick. It's like tribal knowledge. Right. I work with a lot of experienced engineers who know that trick, and they do it on a routine basis. If they know they have a problem with a certain component layout, then they program the pick and place to intentionally skew things, knowing that they're going to self-correct and come back. So that is one way of dealing with this problem as well, if you want to change your pick and place program. But then again, there's a separate program for every job you build. And if you have 100 different jobs that you have to build on occasion, it might be very laborious to go through and change every program.
Right. Might be better just come up with a new stencil. You do that once. Cool. And tribal knowledge is great, but tribal knowledge worries me too, because, if you come from a different tribe, you might have a different way of dealing with it. And that's so hard to document, so hard to teach, so hard to get repeatability, in tribal. What were your main takeaways from this DOE for tombstoning?
Main takeaways were that placement errors were a big contributing factor, especially when we tried to run 0402 and smaller components on our pick and place system. It wasn't really capable to do that. And I think our customers run into that same problem. So that alone will create the issue. Obviously, if you're not placing in the correct position, that's going to create a shift or a skew during reflow. So that's the first place to look when you're combating this problem. Is your pick and place actually placing things off target? And then after that, then we can start talking about stencil designs, which sometimes are a great answer, and they can have a dramatic effect by moving the solder paste or reducing the amount of solder paste with a reverse U-shaped design. And then I'll also talk a lot about reflow profile. That's a good quick go-to that doesn't cost any money. Somebody can add a soak to the profile or lengthen the soak, and that might have an impact. That might affect that. Because of the way boards are designed, typically there's a thermal difference from one pad to the other. And so if you can minimize that thermal difference, that has an impact. And then thirdly, the last answer usually is switching solder pastes, because most customers don't want to do that at the drop of a hat just to solve a problem, because there are other reliability implications there, especially if you're talking about shifting alloys. So in this case, if someone's running SAC 305 and they have customer approval for that alloy, trying to talk their customer into switching that to a blend of different alloys, then there's all these questions that'll come up, like how reliable is that mixture? Is that going to cause any downstream problems later on in the life of this assembly, which are all valid questions. And so that's not always a good answer for folks either, because of those types of concerns. But one of those three things can usually be used to affect this or reduce this defect.
Reminds me, many years ago, I was doing some work with China Lake on their manufacturers committee. That's the old, that Navy Center of Excellence, and that's where the weapons spec 6536 was put into play, and then Mill Standard 2000A. And there was a line, that was cited from there, that when you wanted to do something that was outside of the standard, it was subject to review and disapproval. So I would imagine if you go to a customer and say, "Hey, we got a fix for this. It involves a new alloy." They're automatically subject to review and disapproval, right? No one wants a change.
It's not review and approval.
it's subject to disapproval. Right. It was, very, very pessimistic view. Certainly not an optimistic view. Frequently, when we attempt to solve one problem by making a change in materials or processes, we open the door to, or at least the fear is, we open the door to create yet a new problem. Does the implementation of anti-tombstoning solder paste have any downside? Other than subject to review and disapproval? Are there other attributes of either a blended alloy or just the whatever other technologies in these solder pastes that reduce tombstoning that may not be suitable for something else? Are we kicking the can down the road, or is it completely benign otherwise?
Well, there is that question about reliability of the alloy itself, which is a huge topic of conversation in all of the technical conferences, where we're constantly looking for new, more reliable alloys for different applications. And so when you start switching alloy compositions by using an anti-tombstoning solder paste, then that question comes up. And like I said, that's a very valid concern. Now, of course, in the world of, say, tin lead solder paste, where we see this happening as well, oftentimes we're mixing together two very well-known and long-term alloys that have been in long-term use. So we're mixing together tin lead and a tin lead with 2% silver. And we know each one of those is individually very reliable. And so if you mix together two well-known alloys, it's not as big of a concern for our customers. Right. Now, the other thing that can be impacted is the cost might be affected slightly. Like if you're adding silver to an alloy that doesn't contain silver, like the example I just gave, tin lead with 2% silver is a little more costly than just straight tin lead. And so the cost of the solder paste might go up a little bit.
Right. Nothing's free. The reason I asked that, it reminds me like these pharmaceutical commercials. I love listening to these, pharma commercials, because they say, "Are you depressed? We have a medication that helps solve depression. Might cause bloating, uncontrolled gas, and sore feet." It's like, what? I wasn't depressed, but now I am if I have to take this. But a lot of times there's unintended consequences, but it sounds like this is a pretty benign change. Other than
overall, these pastes perform pretty equivalently in terms of print and reflow performance. It's just the concerns about the cost and the alloy mixture.
Right. And those concerns those are concerns. Those are fear-based concerns. They may not be based on experience. They're just an unknown, right?
Right.
Which is the downside to making a change. Let's talk hypothetical here for a moment. We're going to set you up with a hypothetical. Tony Lentz is creating a circuit board that has to be exceptionally reliable. In fact, if the board fails due to tombstoning or other causes, Tony dies. This board is designed to keep you alive, and you have to design it and build it. So no pressure. What would you incorporate? How would you design the board? What alloys, what materials, what processes for printing would you employ to maintain the longest longevity on this earth?
Well, that's an excellent question. Wow. So I'm going to die if this board fails. So we're talking about a pacemaker or something like that.
It's something like that, yeah.
All right. So I think I would make sure I'm buying high quality laminate materials, first of all, and probably some high T sub G materials, just so they can survive all the reflow temperatures we're going to put them through. I would definitely use a well-known surface finish, something like ENIG, or immersion silver, immersion tin can also be quite reliable. Something that wouldn't have influenced the reliability of the solder joint long-term. And then I'd use well-known alloys. And if I could, I would use tin lead, honestly, just because there's a long-term history of that particular alloy. We know it's very reliable and safe for those types of applications, which is why there's still exemptions for medical devices to use tin lead solders. Yeah. And then in terms of components, I'm sure I would want to make sure that they're not counterfeit, of course, and make sure I'm buying high reliability components from well-known sources. And then I would spec out my manufacturing companies quite carefully, bare board manufacturing and the assembly shop, just to make sure that they're doing quality work and they have quality systems in place.
Sounds good. Well, it sounds like you're going to live a long life, although some of that might be in prison because you're using tin lead, but that's, that's all right.
I thought that was only in California, Mike.
Well, that could be. Well, that's true. Yes, right. You're in what, Colorado, right?
I'm in Colorado.
Oh, you're fine. Yeah, I'm in California.
We like lead around here. We have towns named like Leadville.
Yeah, right. I was saying California, if it tastes good or works well, it's fattening or illegal. It's that's kind of the benchmark. We have there's the AQMD, Air Quality Management District. Many large municipalities have a air quality management district. We have what we call SC AQMD, South Coast Air Quality Management District. And I'm convinced that they have a whole bunch of engineers with calculators on their desk with only 3 buttons on it. Divide, 2, equals. So, because basically they take the federal standard, say the VOC standard, for example, of 50 grams per liter VOC, which is when there is a restriction, that's usually the restriction, 50 grams per liter VOC. In California, in parts of California where we have our special AQMD, it's 25. Just not because they've proven 25 is still functional and beneficial environmentally, but just half, just whatever. If the feds go to 25, we'll be 12 and a half. Divide by 2 equals. That's their job. Just cut everything in half and let us figure it out. So, welcome to California. So get out your crystal ball. Let's end with this, Tony. Get out your crystal ball. What does the future hold for solder paste materials? Where are we going? There seems to be there's a lot of emphasis in IoT and electrification of cars, and there's a lot of attention right now in the context of putting electronics in things that have never had electronics in them before, and of course, wearables and things like that, and then taking them out into the harsh, cruel world. How does that affect solder paste, and where are we going with solder paste? How are we addressing any of these maybe new issues that IoT and electrification of cars is bringing up that we really didn't have in great numbers before?
Well, I see 2 different things happening simultaneously. So first of all, in the world of like cars and automotive alloys, there's a big effort to try to develop high reliability automotive alloys that can survive under the hood kind of conditions. So pretty harsh thermal cycling and also vibration and shock that are occurring. And right now there's Inalot is one of the common alloys that's chosen for that application, but Inalot is not ideal in terms of reflow performance from what I understand. And so there's a lot of different alloys being tested to sort of take the place of Inalot. And they are various combinations. They're tin-based lead-free alloys, but they have things like antimony and nickel and silver and copper, lots of different element additives in order to enhance solder joint reliability. So the high reliability sector is definitely a focus of the future. And then at the same time, we have this move towards low temperature soldering. And the whole idea there is to find lead-free alloys that are as reliable as tin lead, but they solder roughly at tin lead temperatures, maybe somewhere with peak temperatures around 170 up to about 190 or 200 C, which is a tin lead reflow temperature. And so that's being done in order to minimize thermal damage to assemblies, especially with things like flexible circuits, which are a little more thermally sensitive than regular rigid circuit board materials. And so in order to minimize damage to those things, we're moving towards low temperature solders. And it also assists in problems with large size like BGA assembly, where you get some warpage of the BGA and you got head and pillow type defects. That's a real common problem. And low temperature solders can help solve that problem. So that's where I see solder paste technology going. Solder paste fluxes are being developed to work with those new alloys.
There's a slippery slope on both sides of that with temperature, because I'm in the cleaning business, as you know. So from the cleaning perspective, when No Clean first came out, there was issues when No Clean met lead free, I should say. That was not an easy transition, because some of the ultra low solids, no clean fluxes, would polymerize a little too soon in the reflow process due to this higher reflow peak temperature, and not encapsulate the bad actors, the activators and things like that. So you would have unencapsulated metal salts on a board, and that was all blamed on temperature. It's getting too hot too soon, and the flux is kind of polymerizing. And then on the other side of the equation, if the reflow temperature was slightly too low, it wouldn't volatilize the activators, and we end up with higher levels of contamination detected. So there is this kind of Goldilocks principle of just right, not too hot too soon so that we polymerize the flux, and not too cool so we don't volatilize the flux. It's, at least from just a contamination standpoint, that's just one of many reliability concerns. That's an issue, right? Controlling the temperature.
I certainly agree with that. And I saw your presentation on different reflow temperatures and how that affects SIR. I thought that was very interesting data. And in fact, for any of your listeners who haven't read that or seen that presentation, I would highly encourage going and checking that out. But the temperature that we use is necessary in order to make the flux safe to leave on the surface of the circuit board. And because typically when we're testing SIR or ECM, which is the IPC required tests for fluxes, we're doing it at one reflow temperature. We're not doing it with a range of reflow profiles because it's costly and time consuming to run those SIR and ECM tests. And so we're trying to minimize that cost and time, because there's always a demand on chamber time in every lab that does that type of work. So we're running one reflow profile, which is the main recommended reflow profile for the product. But if you reflow a solder paste outside of those conditions, we can't guarantee that it's going to be reliable.
Right. That was the whole point of the article. It wasn't, it wasn't attacking flux or alloys. It was making sure that your process stays in order. People put a lot of effort into setting up a qualified manufacturing process, and then once they get the process down and they say, okay, we're done, they think nothing will ever change and it's going to be golden from here on out. And probably those are the best boards they're ever going to produce, during the actual, qualification process. And it can get a little squirrely after that. So that was the whole point of the article. It was really to emphasize that if you're going to make decisions, for example, in this case, not to clean, which is a fair decision, right? That's a very common mainstream decision, not to clean. And you're going to rely on the original qualification. Better make sure you're still producing boards just like the original qualification. Otherwise, things could change. Well, thanks for the plug on the article. And for those of you who also, right back at you, who would like to dig even more into tombstoning, obviously this conversation can't do that entire DOE justice, particularly with all the visual assets and technical data backing up all of Tony's findings. I'd encourage you to go to the FCT website. By the time this episode airs, that presentation will be on there and available to find. And I will put the links to that article and the FCT website in the show notes. So if you're watching this on YouTube, just look down and where it says show more, click on that, and there'll be a link to Tony's website where you can get that presentation. And if you're listening to this in the car or on the treadmill or wherever you're listening to this, go to your podcast host, whether that be Apple Podcasts, Google Podcasts, Spotify, iHeart, wherever you're listening to this, and look at the show notes, and Tony's information will be there as well. Tony, thank you so much once again for being my guest 30 some odd episodes later. So I can count on you coming back in another 30 or 40 episodes, God willing, if we're still here.
Yeah, certainly. I'd love to do it. Thank you again for inviting me to be on your podcast. I appreciate that.
Well, always good to talk to you. And hopefully we'll get back to producing some live events sometime in the near future.
Yeah, that would be great. I would enjoy that.
I like looking at people. I had the luxury of being able to speak at the Cleaning and Coating Conference in Dallas earlier this year, or a couple months ago, and then again in Minneapolis at SMTA. And it's so nice to actually look at people, not pixels, and get a real human interaction. So I'm looking forward to more of that coming up in 2022.
I agree. I'm looking forward to that as well. And I hope the pandemic will allow us to do that a little more next year.
Yeah, same here. Well, thanks again, Tony. Good, as always, talking to you. And I hope to see you again in the near future.
I hope to see you again soon as well, Mike. Thank you.
You bet. Thanks for listening or watching the Reliability Matters podcast. Be sure to subscribe to the podcast on your favorite podcast app, such as Apple Podcasts, Google Podcasts, Spotify, and so many more. Also, be sure to check out my other podcasts, including the Concept to Creation podcast, where I feature conversations with entrepreneurs within the electronic assembly space, and the Innovations in Technology podcast, where we discuss innovative products within our industry. All three shows are also available in video format. Check out the Reliability Matters or Concept to Creation or Innovations in Technology podcasts on YouTube. Just search the show's name and you can find all three shows. Or go to mikeconrad.com, that's Conrad with a K. All three shows also appear there. Again, thanks for being part of my podcast family. I appreciate you being here. Until next time, stay safe, stay healthy, and stay happy. And of course, keep doing it right. See you again soon.
Thanks for listening to the Reliability Matters podcast. Join us on the second and fourth Tuesday of each month for new episodes of Reliability Matters.